We actually did it. We detonated a nuclear bomb in space. Not near space, not the edge of the atmosphere. Right there. In the void, above the Earth. A full-on, multi-megaton nuclear blast, floating 400 kilometers up, where satellites orbit and the aurora shimmers. And we didn't just do it once, we did it multiple times. It wasn't an accident. It wasn't a weapon test gone wrong. It was deliberate, planned, and followed through without fully understanding what it might do. And for a few brief moments, it looked beautiful. Blinding light, glowing skies, artificial auroras painting the night like something out of science fiction. But the aftermath? That wasn't so beautiful. Within minutes, satellites began failing. Some permanently. Within hours, electronics thousands of kilometers away short-circuited. And within days, Earth had something it never had before. A man-made radiation belt, circling the planet like a glowing trap. If you've never heard of this, good. That means it hasn't happened again. But it almost did, and it still could. Because when we nuked space, we didn't just test a bomb. We tested what would happen if we treated space like it was empty, and it's not. And the truth is, we broke more than we realized. So let's talk about the moment we nuked space, and the huge problem we created that still haunts our skies. So here's how it actually happened. On July 9th, 1962, the United States launched a Thor missile from Johnston Atoll, an isolated strip of land in the Pacific Ocean. Its destination, the edge of space. It carried a nuclear warhead, a 1.4 megaton bomb. That's about 90 times more powerful than what was dropped on Hiroshima. And the target wasn't a city. It wasn't an enemy. It was the space above Earth. At exactly 400 kilometers altitude, roughly where the International Space Station orbits today, the bomb detonated. This test was called Starfish Prime. And to be honest, even the scientists behind it didn't fully know what would happen. They had theories. They wanted to study how nuclear explosions behave in the vacuum of space. They wanted to see if it would disrupt communications, create auroras, or interfere with satellites. When the bomb went off, the sky didn't go black. It lit up. Observers reported a sudden, blinding flash that turned the night sky bright as day for a moment, followed by auroral displays. Newspapers and personal accounts from Honolulu described the sky glowing vividly, with some mistaking it for a natural phenomenon, or even a fireworks display. People in Hawaii, over 1,400 kilometers away, saw the explosion. Not just a flash. The entire sky shimmered in strange colors. A green and red glow spread across the horizon, like someone smeared paint across the stars. It wasn't fireworks. It was a side effect of dumping insane amounts of energy into Earth's magnetic field. Electrons, stripped from atoms, started spiraling along the magnetic lines like a chaotic light show. But here's the twist. While people on the ground were staring at the sky, the real damage was happening in silence. Approximately 400 kilometers below the explosion, streetlights in Hawaii suddenly went out. Telephones stopped working. Alarms were triggered. It looked like nothing had happened. No fireball, no blast wave, but electronics were fried. This was the first time anyone had really witnessed the power of an electromagnetic pulse in action. And above the Earth, things were even worse. Satellites, some launched only months before, were passing through a radiation zone that hadn't existed the day before. Because that's what Starfish Prime did. It created an artificial radiation belt, like a new man-made version of the Van Allen belts that naturally exist around Earth. Except this one was unstable, chaotic, and deadly to anything electronic. The artificial radiation belt damaged or destroyed several satellites at the time. The high-energy particles degraded solar cells, transistors, and other electronic components, causing gradual failures. And over the course of weeks, they started dying, one by one. Telstar 1, one of the most advanced communications satellites of its time, was launched just one day after the test, Within months, it began to experience problems. Other satellites, Ariel, Transit 4B, and more, were knocked offline or permanently damaged. It was like launching new tech into a minefield no one knew was there. And while Starfish Prime was the biggest, it wasn't the only one. That same year, the US conducted a series of high-altitude nuclear tests under Operation Fishbowl. Smaller detonations. Same idea, same risks. At the same time, the Soviet Union was doing their own version, Project K, detonating nukes above Kazakhstan, causing power disruptions over huge distances. Both sides wanted to understand the military implications of nukes in space. Could they blind enemy satellites? Could they disrupt communications or disable incoming warheads? The answers turned out to be yes, yes, and yes, but also they could disable your own satellites too. So back in 1962, we nuked space, repeatedly, and we thought we were learning. But what we were actually doing was breaking something we didn't fully understand. And the long-term effects? Not well understood, even today. And this brings us to the next problem, the hidden radiation belts we accidentally left behind. So here's what most people didn't realize back then. And honestly, what most people still don't know now. When we nuked space, we didn't just create a light show or knock out a few satellites. We created something that stayed, something invisible but dangerous. You've probably heard of the Van Allen belts, those natural zones of charged particles trapped by Earth's magnetic field. They're part of why we don't just send astronauts into space casually. Radiation builds up there, and it's not friendly. But after Starfish Prime, scientists realized they had accidentally made a new belt, one that didn't exist before. A glowing artificial ring of high-energy electrons wrapped around the planet. And it was completely our fault. When the bomb went off, it released a burst of gamma rays and energetic particles. These particles collided with atoms in the upper atmosphere, knocking loose electrons at extreme speeds. Because of Earth's magnetic field, those electrons didn't just scatter, they got trapped, looping around the planet again and again, forming a shell of artificial radiation. This belt didn't fade away quickly. It lasted months. Some traces of it remained years later. Satellites that weren't designed to handle that level of radiation started to glitch. In total, at least 7 satellites were seriously affected. Some of them were the most advanced technology of the time. And here's the messed up part. These satellites weren't even in low Earth orbit. They were in medium Earth orbit, areas previously considered relatively safe. But that safe space was now filled with deadly radiation that wasn't there before the explosion. You know how modern satellites are hardened against radiation? Yeah, this is where that started. Because back then, they weren't. The radiation would slowly seep into the electronics, messing with transistors, degrading solar panels, scrambling data. And the worst part, there was no way to fix it. You couldn't fly up and patch them. You couldn't reboot from the ground. Once a satellite got hit too many times, it was done. Now imagine the bigger picture. Earth is surrounded by this delicate shell of satellites. These satellites are not just tools in space, they are extensions of human civilization. They allow us to observe Earth's climate, track storms, guide aircraft, manage global communications, monitor borders, and operate military systems. And we just dropped a radioactive cage around them. That's not just damage. That's interference with Earth's ability to observe itself, to talk to itself. And the radiation belts weren't just isolated to space. Some of those particles got knocked down toward the upper atmosphere, messing with radio signals, altering the ionosphere, even disrupting long-range communications on Earth. It was one of the first times we saw how tightly linked space and Earth actually are. Mess with one and you affect the other. It's not a vacuum, it's a chain of systems, all connected. And all of it started with one explosion. We thought it would just be a test. What we got was a reminder that space isn't empty. Back then, in 1962, nobody had heard of the Kessler Syndrome. There was no reason to. Space was mostly empty, satellites were rare, and no one really thought about what would happen if things started crashing into each other up there. But that changed slowly after Starfish Prime. See, when that nuke went off, it wasn't just radiation it unleashed. It created chaos. Satellites got damaged, circuits fried, electronics failed, and some of those satellites, the ones that lost control or power, became nothing more than fast-moving junk. Orbiting wreckage. Dead weight. And here's the thing about junk in orbit. It doesn't just stay still. When something breaks in space, it keeps moving. Fast. Like 28,000 kilometers per hour fast. And if it collides with another satellite, it doesn't just bounce off, it shatters. The impact creates more fragments, each of which becomes another threat, another shard flying around the planet. That's what the Kessler Syndrome is about. First proposed by NASA scientist Donald Kessler in 1978, it warns of a future where space becomes too dangerous to use. The more debris we add to orbit, the higher the risk that one collision triggers another, and then another, setting off a runaway chain reaction of destruction. Over time, this cascade could fill Earth's orbit with a cloud of high-speed wreckage, threatening satellites, space stations, and future missions. Entire orbital zones could become unusable, not for years, but for decades or even centuries, leaving us trapped beneath a halo of our own making. Now, nuking space didn't start the Kessler Syndrome, but it pushed us in that direction. We showed how easy it was to destroy satellites from afar, and once you destroy a satellite, intentionally or not, you're adding to the growing cloud of orbital debris. Think about this. All it takes is one disabled satellite drifting out of control to clip another one. And then those two shatter into thousands of pieces. Some of those pieces go on to hit more satellites. The worst part? We wouldn't even be able to stop it. There's no cleanup crew in orbit, no giant net, no way to just pause the traffic and fix things. Once the chain starts, the only option is to wait, decades or longer, until the debris naturally falls out of orbit. That is, if it ever does. This is why modern space agencies track every piece of debris larger than a marble. Because it doesn't take a missile to cause a disaster, just a fragment. Just one screw or paint chip moving fast enough can punch a hole through a satellite. And imagine this today. We have thousands of satellites up there. Starlink alone has over 7,000. Then there's GPS, military satellites, weather monitoring, Earth science missions, communications satellites, and the International Space Station. One mistake, one detonation, one lost satellite, one bad collision could set off a chain that wipes out dozens of systems in a matter of hours. It doesn't even have to be nuclear anymore. But the lesson we learned from nuking space is this. When you mess with the environment up there, you don't just cause damage, you create risk, lasting risk, generational risk. And if Kessler Syndrome ever happens on a large scale, we could be locked out of space entirely. No launches, no satellites, no missions, just a planet surrounded by its own failure, with no easy way to escape it. All it takes is one event. And now, with rising tensions, new weapons, and increasing satellite traffic, it's not just about what happened in the past. It's about how close we are to repeating it. After the chaos of 1962, the message became clear, even to the people in charge. Nuking space was a bad idea. It didn't win wars. It didn't make us safer. It broke things we didn't know we could break. So, in 1963, just 1 year after Starfish Prime lit up the sky, something historic happened. The Partial Nuclear Test Ban Treaty was signed by the US, Soviet Union, and others. It banned nuclear explosions in the atmosphere, underwater, and crucially, in outer space. This treaty, still in force today, was a pivotal geopolitical outcome, driven by the recognition of risks to global communications and space infrastructure. This wasn't just politics, it was survival. Scientists had seen what happened when we detonated a nuke 400 kilometers above the Earth. The artificial radiation belts, the satellite failures, the EMPs that reached across oceans. The threat wasn't hypothetical anymore. It was real, and it wasn't just the United States. The Soviet Union had seen it too. Their own high-altitude tests under Project K had caused blackouts and communication failures across parts of Kazakhstan. They realized they weren't immune. The space age was still young. Nobody wanted to destroy it before it began. Then, in 1967, another treaty followed, the Outer Space Treaty. This one laid the groundwork for all future space activity. It said no one could claim the moon. It said space had to be used for peaceful purposes. And most importantly, it banned the placement of weapons of mass destruction in orbit or on celestial bodies. For a while, it worked. For decades, no one tried to detonate a nuclear weapon in space again. Not publicly, anyway. We stuck to scientific missions, communications, satellites, and peaceful exploration. Sure, the Cold War played out on Earth, but space stayed relatively calm. But lately, things are shifting again. There's been a quiet build-up, not with nukes exactly, but with anti-satellite weapons, or ASATs. Multiple countries, including the US, Russia, China, and India, have developed and tested systems that can target and destroy satellites in orbit. Some tests have already happened. In 2007, China destroyed one of its own weather satellites in orbit, creating over 3,000 pieces of trackable debris, with estimates suggesting tens of thousands of smaller untracked pieces. In 2019, India did something similar, launching a missile to destroy a satellite and adding to the growing cloud of junk up there. Russia has tested direct ascent anti-satellite weapons, some of which come dangerously close to operational satellites. None of these used nukes, but they showed something else. We're getting comfortable again with breaking things in orbit. And here's where it gets worrying. The idea that nations now have the potential to develop space-based military technologies is deeply unsettling. These are not just theoretical advancements. They carry real-world risks. If even one of these systems were to malfunction or is used recklessly, it could put us right back in the same position we were in during the early 60s. This time, though, it would be worse. Because now space isn't empty anymore. It's crowded. We rely on it for everything. GPS, internet, banking, TV, defense systems, climate data, disaster warning, crop monitoring, airline navigation. You name it. If a single detonation or a single weapon took out even a portion of that network, it wouldn't just be a problem for scientists. It'd be a problem for everyone, instantly. And that's what makes it so dangerous. We already made the mistake once. We already lit up the sky with a bomb that broke our orbit and taught us how fragile our systems really are. But the more we militarize space again, the more we act like those lessons don't matter. It's not that people want to nuke space again. It's that the next disaster might not need a bomb. It might just need one country pushing too far. Let's not sugarcoat it. If someone nuked space again today, just once, it wouldn't be like 1962. It would be worse. Way worse. Back then, we had maybe a couple dozen satellites in orbit. Now, we've got over 11,000 active satellites, and that number's growing every month. Starlink alone plans to launch thousands more in the coming years. We've packed space with everything: communications, weather monitoring, GPS, military surveillance, internet services, banking infrastructure, climate science, you name it. And there's a satellite up there making it work. Now imagine one nuclear detonation at the right altitude, say 400 kilometers, just like Starfish Prime. That's the same region where thousands of low Earth orbit satellites operate. It's where the ISS floats, where Earth imaging satellites scan coastlines, where defense and early warning satellites keep tabs on global activity. A high-altitude nuclear blast would send out a massive EMP, just like before. But now it would hit everything. Thousands of satellites, all suddenly exposed to radiation they weren't designed to handle. Solar panels would start degrading almost instantly. Circuits would fry. Communication systems would drop offline. Navigation data would go dark. And here's the kicker. You wouldn't get a warning. No countdown, no shockwave, just silence. Suddenly, systems stop working. Flights lose GPS. Banks can't process transactions. Ships in the middle of the ocean can't navigate. Power grids get weird. Some phones go out, some don't. It would feel random, glitchy, until people realize it all happened at once. And the chaos wouldn't stop in space. If the EMP is strong enough, it could reach Earth's surface. Again. It could knock out transformers, trip power stations, damage underground cables. Not globally, but in large regions. Even a partial blackout of GPS would affect every industry that depends on timing, from stock markets to farming. But let's go beyond the EMP. The explosion would inject a huge number of high-energy electrons into Earth's magnetosphere, just like before. Only now, with more satellites and tighter orbits, those artificial radiation belts would become a death zone for spacecraft. New satellites trying to launch, they'd be flying into an invisible radiation minefield. Missions could be delayed for months or years. Anything unshielded would degrade faster, fail faster. Even the International Space Station could be affected. And the worst part, the debris. If even a few large satellites break apart due to radiation damage or system failure, their remains become space junk. Fast-moving, uncontrollable debris. One satellite shatters into hundreds of fragments. Those fragments start colliding with others. And just like that, we're in Kessler Syndrome territory, where space becomes so polluted that launching new missions becomes too risky to even try. So, what would it actually look like if we nuked space today? GPS blackout, global communications outages, commercial airline navigation failures, military surveillance gaps, weather prediction loss, possible regional power disruptions, billion-dollar satellite losses, years of degraded access to orbit, all from a single detonation. Not because it hit anything directly, but because in space, indirect damage is just as dangerous and usually harder to fix. It's like setting off a bomb in a server room. You don't have to destroy the building, just kill the systems that keep it running. We've built a civilization that depends on what's floating above us, and it takes just one mistake to unplug the entire thing. Here's what's strange. We nuked space. We created an artificial radiation belt. We knocked out satellites. We caused power outages across continents. We damaged systems still being built. And most people have never even heard about it. That's the scary part. If someone asked you what the most dangerous human-made event in space was, you might say a rocket explosion or a satellite crash. But a nuclear detonation in orbit? That wouldn't even cross most people's minds. And yet, it happened. In real life. And the consequences weren't just immediate, they echoed for years. So, why don't people talk about it? Part of it is simple. The damage was invisible. There was no crater, no fallout cloud drifting through cities, no footage of flattened buildings or mushroom clouds on the horizon. The effects happened in silence. Above us, in orbits we couldn't see, and systems most people didn't understand yet. When Starfish Prime exploded, there wasn't any screaming headline like "Space nuked, satellites dead." It wasn't something people could point to and say, that was the moment everything changed. But it did change. We just didn't feel it all at once. The radiation belt it created slowly damaged spacecraft. The EMP quietly fried electronics. The satellites died days, weeks, and months after the detonation. The connection wasn't obvious to the public. It didn't feel like an attack. It just felt like technology was failing. And back in 1962, most people didn't rely on satellites anyway. GPS didn't exist. The internet hadn't been born. Even long-distance communications were just starting to go global. So, when things failed, people noticed, but they didn't panic. Now though, if the same thing happened today, it would be different. Every part of modern life depends on space. From the phone in your pocket to the plane flying overhead to the card reader at the gas station. Even if you don't see a satellite, it's still quietly holding everything together behind the scenes. And if someone decided to detonate a nuke in orbit now, the damage wouldn't be invisible anymore. It would be immediate, tangible, expensive, and global. But most people still don't know that. They don't know how fragile the system is, how interconnected it all is. They don't know that a single event could affect banking, aviation, defense, internet access, emergency response, and more, all at once. This is what makes it a quiet crisis, not because it hasn't happened, but because it did, and we forgot. We learned the hard way what nuking space does. We saw it, measured it, counted the dead satellites, and then we moved on. Now, as countries develop new weapons, test anti-satellite systems, and explore nuclear-powered space tech, that history feels dangerously forgotten. The lessons are still up there, orbiting, waiting. We don't usually think of space as something you can break. It feels too big, too distant, too cold. You hear nuclear explosion in orbit, and it sounds like science fiction. Something dramatic, sure, but contained, out there. But the truth is, space is connected to everything down here. It's not just where satellites live. It's where our eyes are, our maps, our clocks, our weather reports, our global communication, our defense systems, our economy, even the ability to call someone on the other side of the world. All of it depends on satellites working in silence, far above the clouds. When we nuked space in 1962, we didn't know what we were really doing. We were testing limits, proving power, trying to understand a new frontier. But what we actually did was show how fragile that frontier is. One explosion created an artificial radiation belt that lasted years. It killed satellites, damaged electronics, and pushed science decades ahead, because we learned how dangerous space could be, the hard way. We saw how energy unleashed above the planet doesn't just stay up there. It ripples downward. It interferes with Earth's magnetic field. It scrambles systems we thought were protected. It creates problems we can't solve quickly, or at all. And the worst part? We're still close to doing it again. New tensions, new technologies, new weapons, anti-satellite tests, military satellites shadowing each other in orbit, treaties being questioned, space getting more crowded by the day. It wouldn't take much. Not a war, not a world-ending event, just one mistake, one detonation, one decision that puts ego or control above reason. And we'd be back to square one. Except this time, it wouldn't just cost us a few satellites. It would cost us the systems our world depends on. That's why this story matters. Not because it's dramatic, but because it's real and forgotten. We nuked space, and we learned something that still applies today. Space isn't empty. It's not invincible. And if we break it again, we may not get the chance to fix it.